Hi everyone, welcome to the channel. Today we'll be looking at this problem called word search, and I'll be going through how I solve the problem and the process. And if you're new to the channel, what is here is I go through different software engineering interview questions and I explain how to use various technologies. Be sure to also check out my website and follow me on social media. All the links are in the description below. And on the website and social media, I'll make posts on social media so you know when the latest videos on YouTube are posted, as well as the latest blog posts on my website. And then on my website, I have supplementary materials for some of the YouTube videos, so look out for that. And also information on how to use various technologies. So yeah, if you're interested, please subscribe, follow, and share with other people who you think will also find it interesting and will benefit from it. Without further ado, let's continue with the problem. So in word search, we have a 2D board and a word. We want to find if the word exists in the grid. And the word can be constructed from letters of sequentially adjacent cell, where adjacent cells are horizontally or vertically neighboring. Same letter cell may not be used more than once. So we see this board here. And we want to see A, B, C, C, E, D, and it's true because it can be found. So let's see. Okay, since you can move adjacent, I see A, B, C, C, E, D is the solution, and then S, E, E, that's another solution, so return true, and then A, B, C, B, so yeah, there's only one B, so there's no way to do it. And good clarification questions would be asking about constraints, but for this one, I think it's, since I solved this problem already, it's safe to assume that within the board, everything is a letter, so we don't need to check that, and everything is a capital letter, so there's no need to, well, actually, I'm not sure if that one's true. But our algorithm, it will be generalizable, so it's matching every letter from the string, so even if it's a number, it will still work for our algorithm, so that's fine. And so this type of problem can be solved with backtracking. And the reason why I say backtracking is, suppose we have A, B, C, C, E, D. We know that since we do not know which element within this grid is the starting letter, first thing we have to do is we have to scan through the entire board. And at each point when we go to the board, let's say we are searching for the string A, B, C, C, E, D, then we need to find all the positions that have A and then call our backtracking algorithm on that letter. And the other thing that we don't know is for each position that we call the backtracking algorithm, we don't know which direction or if any direction will yield the correct solution. So we will also need to check the 4 directions because those are the directions for adjacent. So an example would be, let's say I'm looking for A, B, C, C, E, D. I check all the elements. Every time I see A, I call it backtracking. Once I call it backtracking on A, I know that the first letter is correct, but I don't know if B will exist on the right, on the top, on the left, or the bottom. So that's why I need to make 4 calls at each point in time. Any of them could be wrong. If it's wrong, then I'll backtrack and stop the search. So if I move down, I see there's S and we're looking for B. Since A has already been matched, then I backtrack and I return. That way preventing the further search starting from A and going downwards to look for A, B, C, C, E, D. So that's why backtracking is used for this type of problem. One other thing that we noticed is, as I was talking about the 4 directions, we also need to check if the spaces are inbounds for each step of the backtracking algorithm. And in terms of how to do the search, we know that we can do depth first search or breadth first search. And for this one, since each position we're going to go into a specific direction, we'll be doing breadth first search. We'll be doing depth first search, and the reason being that once we do depth first search, let's say I choose right, we have this combination A, B, C, C, E, D. This returns true, and then we will return the solution here at this call rather than continuing to expand. So for starters, we can write what we said initially, which is we need to find the correct cells to call the backtracking algorithm on, and so that will involve iterating through the entire board. So to do that, we get the number of rows within the board, as well as the columns. And now we have the row and the column. We would also like to have a way to keep track of what cells we have visited. And so we need to make a visited matrix. Now we have our visited matrix, and now we iterate. All right, not semicolon, we have to do a colon. And then we check if board RC, if that element equals the first letter. Sorry, not board 0, word 0. And if it is, and an edge case is if the length of the word is 1, then we will return true because we have found the entire word where the word is 1 letter. Otherwise, we mark this position as visited. And we need to write our backtracking algorithm, which we'll call search. And if we search from that position and it's true, then we return true. And because it's backtracking, we will then make this position 0. And we can see, here's an example. Let's say we're looking for AD. Let's say, suppose the word, search or word equals AD. So if we're looking for AD and I search through the matrix, right? And then I'm here, I'm like, oh, I see A. So I call the backtracking search algorithm. And then it searches and it's like, all right, so it looks as B, looks as S, out of bounds, returns false. At that point in time, this position A is marked as true. Or let's say what else? Well, there's no guarantee that this, after this is marked as true, that it can't be the end of a the end of a word. So I think a better example is AB. So if I have AB and then I search through once, or if I'm looking for BA, well, I suppose AD is not a bad example. But what I was getting at is when you mark something as visited, you want to unmark it because it could still be part of another word that's searched later. So just because AB is not just because A is searched as the first word, it becomes marked as visited, but it doesn't mean that later you don't want to visit as you're doing the backtracking algorithm for subsequent directions and also for subsequent starting positions within the board. And if we are unable to find anything, then we return false. So now for our search, as we're doing our search, there's a couple of things that we need. So we'll definitely need to send in the board, and we'll need to pass in the visited matrix so we know what has been visited, and we pass in the word and the row, the current row, current column, and then the maximum row and maximum columns that we should be searching. So the call for this, put in the board, we put in visited, and since the first letter has been marked as visited, it means that we are now searching for the rest of the word, and then the current row, current column, and then the maximum row, maximum column. Well, maximum plus 1 since Python 0 index, so when we get the row we see 2 rows, but we go the index 0 to 1. Now the base case is if we have no word to search, then it means we have finished finding every single word, and now we have finished finding every single letter within the word on the board. And then because we're doing backtracking and we're calling for directions, we initially say all 4 directions are false unless we perform backtracking in that direction and we find something, and then that will get updated. Now the 4 directions are very similar. All of them we need to check if it's inbound. So first thing, let's check top. So to find top or up, we check if the row above is greater than or equal to 0, because that's what will make it up inbounds. And we also check if it's not visited, -1, C, and word. So we check if the first letter equals what is on the board 1 position above. If it is, then up.self. We recursively call our backtracking algorithm. And we'll look for the next letter since this current letter has now been visited. And then to update the current position and the row column, we continue to pass that. And then if up, we return true. Well, let's see. Looks like I did not mark it as visited. Oh, right. I have not marked it as visited yet, which I should. Yeah. And yeah, we can see why we need to change visited back to 0, since you could search for, let's say it's a 10-letter word. We found 7 letters, and then the other letters cannot be found from that path. And so you need to, let's say we find this path here, and then there's some letters that were not found afterwards. You have to clean this path up, and then you start at the next position to start the backtracking algorithm. So you always have to constantly clean things up, even for other directions as well. Okay, well, let's see. So we check up, then if it's visited and the word matches is found on the board, then we mark it visited, and then we call up, and if that's true, we return true. Else we continue with our algorithm. So now we copy and paste this, and we have 4 directions. So another direction we could do is down. So for down, it would be +1, and then here we would change to +1. And for the board as well, we would change to +1. And yep, let's change all the -1s to +1. And instead of up, it has to say down. Right? Now we could do left. So left has to involve the C now, instead of have to change that back. And this is left. All right, last direction is right. If we search all for directions and we're unable to find a direction, then yeah, we will return false. And to clean up the code, we can have it return false here if the four directions don't work, and the up, down, left, right is actually unnecessary, so we don't need that. And yeah, I guess one thing would be to run through the code, make sure it's working. So we get submit, but let me read over it first. So row, column, board 0. This is your 5 range column. For J in range row, rows, column. Check every position, see if the first letter matches. If the length is 1, return true. Mark it as visited. Then we call search and return true. Okay. Now, if we have empty word, return true, since we found all the other letters in the word. And then check left, or check up, as r minus 1. If we didn't visit r minus 1, and it's equal to the first letter is equal, next letter, which is the first letter, is equal to r minus 1. C, mark it as visited, r minus 1c, that's up, up, r minus 1c, r plus 1, that is down. So r plus 1c, r plus 1c, r plus 1c, r plus 1c, down, down to r plus 1c, and then rc minus 1. Okay, so this is left. rc minus 1, rc minus 1, visited, rc minus 1, left. Okay, and then we backtrack, so mark it as 0, and then rc plus 1, this is right. So rc plus 1, rc plus 1, rc plus 1, mark it as visited, recursive call, c plus 1, and then, all right, cool, looks good to me. Let's see if it's, okay, so, all right, we got some runtime error, line 13. What's happening here? List index out of range. Oh, okay. I think it's because, yeah, I have to adjust the inequality. So when you do -1, you have to make it greater than or equal to 0. And then whenever you're adding, you have to make sure, since we're doing rows, it has to be less than or equal to row. So similarly, c minus 1 greater than or equal to 0 is good. But then here, it would have to be less than or equal to the column. Okay. Oh, right. So it would, the maximum number of rows, let's say you have 2 rows, then the indices would be 0, 1, since Python is 0 index. So doing less than or equal to means if I have 2 rows, then it would try to index 2, which would be incorrect. It should only index up to 1 for 2 rows. All right, great. Wow, this code is dang fast, man. Faster than 100%. Okay, anyways, so talk about runtime for a little bit, which is we need to iterate through each of the positions in the board. And let's say there's m rows and n columns. So that would be m times n, since we need to go to each position. And then m times n, once we go to each of those positions, we are going to search the board. And the worst case is the entire board gets searched. And so that would be m times n. So each call from the m times n, at worst, it will search every single letter on the board, which is m times n. But once it searches that, no buts. So I think the algorithm would be m squared, n squared. Yeah, m squared, n squared for the runtime, and then for space complexity, it is m times n, since I need to store the visitor array. All right, thank you guys so much for your time, and hope you all learned something. If you find this useful and want more content, please like and subscribe and share with anyone else you think will enjoy this content. Be sure to check out my website and follow me on social media for the latest updates. All right. Thank you, everyone, and enjoy the rest of your day.